Um, Today's lecture is about how we solve rational expectation models, that is linear rational expectation models, both with current expectation and with future expectations in them. But before I formally start a discussion of how one can solve these type of models, I need to digress and discuss the properties of conditional expectation, which I need to use in the lecture, and also the concept of martingale and the properties of martingales, in case some of you are not familiar with them. Firstly, for our purposes, if we define the information set omega t as being including all the information, say, available on xt, y to the past, or if there are other variables which we can denote as yt or yt minus 1 and so on, then we can define an increasing sequence of information sets, omega 1, omega 2, and so on to omega t. These are all increasing fields of information. And that's what we need, in a sense that omega t includes information set omega t minus 1, omega t minus 1 includes information set omega t minus 2, and so forth. With respect to this set of information set, we can then define conditional expectation of, say, yt, conditional on omega t minus 1, or we can define, as we discussed before, conditional expectation of, in general, yti, conditional on information set omega t minus j. From now on, I'm assuming all these conditional expectations exist. If we do not exist, we cannot even start looking at these models. And the second property, so that's they exist. If we start now looking at the properties of this type of conditional expectation, it's all standard results. The first says that a conditional expectation of a constant relative to the, say, information set omega t minus 1 is equal to the constant. The second is that conditional expectation of a weighted average of, say, if you had a number of variables yti instead of 1, conditional omega t minus 1, again, omega t minus 1, including all information on all the y's up to t minus 1, that would be again equal to sum of expectation, ai expectation of yti given omega t minus 1, I from 1 to, say, k, and the same here. That's the sort of, we can take expectation through a linear combination. Now, furthermore, if we have yt being positive or equal to 0, a non-negative number, then it would also follow that expectation of yt conditional on omega t minus 1 is also positive, non-negative. It's essentially, since all yt's are positive, it's a property of expectation. The fourth one is not as obvious as the previous one, but it's not difficult to prove. And he says that expectation, absolute value of expectation of yt conditional on omega t minus 1 is always less than or equal to the expectation of absolute value of yt conditional on omega t minus 1. Now, if you had a different colored chalk, it's remember, this is the absolute value, and that is the conditional expectation. I mean, in fact, you don't want to confuse the two. Okay? Now, these are the general, comes from the general property of conditional expectation. Let me just give a very short proof of the last one, because we are going to use it later on, so you know where this comes from. It essentially is like, you know, assuming that the absolute value of the integral is less than, sort of if you take the absolute value inside the integration, but it's for the conditionality is a bit more complicated. Is this proof covers this? Suppose we have got yt, set yt is minus yt. This is always positive. This is positive. Either yt is positive, therefore is 0, or if it's negative, the whole of it positive. The same, we have also that yt plus yt is also non-negative, by definition. Now, if we use this property, it follows, therefore, that, if I may write it here, it follows, therefore, that expectation of absolute value of yt minus yt, conditional omega t, has to be also non-negative. And the same goes for when we replace it by a positive sign, omega t minus 1, omega t minus 1. That is also positive. So from that, it follows that expectation of yt, the absolute value, conditional or omega t minus 1, has to be always larger than either that minus expectation of yt conditional omega t minus 1 or plus expectation of yt conditional omega t minus 1, so therefore is larger than their absolute value. Is larger than either its positive or negative value, which establishes that is always the case. Now, these are all just properties of conditional expectations. And since the rational expectation model essentially assumes that expectations are mathematical expectation conditional to some information set, so it also follows that the rational expectation variables also satisfy all this conditioning. It follows from that notion of definition of what rational expectation is. Now, apart from these, there are 3 other properties which I will be using later on, and it's crucial to a study of rational expectation hypothesis. These are usually referred to based on the law of iterated projection or iterated expectation, the orthogonality property, and the property of no serial correlation of the expectational errors. Now, I'll just go through them very quickly. Hopefully, most of you are familiar with these. Now, the first one is essentially saying that expectation of xt, say conditional on omega t minus 1, and then conditioned on omega t minus j, is equal to expected value of xt conditional on omega t minus j for all j larger than equal to 1. Now, what it says essentially is this, that if I have an expectation which I held at time t minus 1, and then I want to look at what I would have expected for that expectation at time j period before, it said there is no reason that I would have changed it because I have no other information. When I'm deciding at time t minus j, concerning what I would expect at time t, if I knew the information at omega t minus 1, it should be the same as what I would have expected at time t minus j. Now, this is, again, a property of expectation, mathematical expectation. And it follows from the fact that omega t minus j omega t minus 1 includes omega t minus j. You can, in fact, write a more general expression. I just write it for you, that you can write it as expected value of t plus I plus j given omega t plus I conditional at omega t minus L. This is also equal to expected value of x t plus I plus j conditional omega t minus L. You can write that as well, for all I and j being all non-negative. This is sort of the law of iterated expectations. Now, the let me just give an example to give life to these things. Suppose you had xt was a first order autoregressive process, where epsilon t's are white noise, and there is some rho which is fixed. Now, what is expected value of xt given omega t minus 1? Here is rho xt minus 1 because we are assuming that epsilon t's are white noise. Okay, now suppose I take expectation of xt given omega t minus 1 given omega t minus 2, just for the sake of argument. According to this rule, it should be just expectation of xt given omega t minus 2. Okay, we can actually check it by calculating, because we know what the expectation of xt given omega t minus 1 is. It's given rho xt minus 1. So this has to be also equal to expected value of rho xt minus 1 given omega t minus 2. Because from here, that would be exactly that. Okay? So we can now say that's equal to rho expected value of xt minus 1 given omega t minus 2. Remember, we can take the constant out. And from that, this is the same, is based on the conditional expected t minus 2, so that has to be equal to rho xt minus 2. So the whole of this expression becomes rho squared xt minus 2, which would be exactly the same if we directly went and calculate that. So it's useful for when you want to take expectation in iterated way. It helps you in that sense. You can give other examples. One can give other examples which shows how we can use this sort of iteration. But later I'm going to use it when I want to look at a method of solution which is called forward operation or forward-looking type solutions. Now, the orthogonality property comes to do with from the fact that if I define xi t is the expectational error of yt, say, let's define it with respect to omega t minus 1, then the orthogonality property suggests that xi t is orthogonal to any set st so long as st is included in omega t. Sorry, st minus 1. Now, the fact that when this is also orthogonal to the whole information set available at time t minus 1 follows as well. And this again follows from the iterated operation that we talked about just a minute ago. To prove it, you just simply calculate relative to st minus 1. That gives us expected value of yt given st minus 1 minus expected value of yt given omega t minus 1, all of that given st minus 1. But we have just, that is therefore is equal to yt given st minus 1 minus, since st is already included in omega t minus 1, applying the rule of iterated projection, that has to be equal to yt conditional on st minus 1. We had an example of it here, so that the whole thing has to be 0. Now, again, when we come to talk about the testing of efficiency of the market hypothesis and various other hypotheses concerning rational expectation, this property plays a very crucial role. In fact, it is this property together with the property of serial correlation which has been often used in order to test the rational expectation hypothesis in general. Now, it follows from this property also that any information set available at time t minus 1, which is in the set st or a set omega t, multiplied by the expectation error should be also orthogonal to the information set. Just for the sake of argument, expected value of ET minus xi minus I, xi conditional omega t minus 1 should also be 0. Or for that matter, expected value of conditional on a subset of omega t should also be 0. Now, why is that the case? Now, the first one is, we can just demonstrate very quickly that since, I larger or equal to 1, since xi t minus I, which is the expectational error, will be known, and it will be therefore in the information set omega t minus 1, so it is a constant given to the information set. It comes out. So it becomes, let me just wipe this off for a minute. Then we will have t minus I expectation of xi t omega t minus 1 equal to, but that is 0, so therefore the whole thing becomes equal to 0, irrespective of what this value is. Now, one of the things, another property which we haven't talked about, that if you have a conditional expectation equal to 0, say xi t minus I, in this case xi t given omega t minus 1 is 0, is unconditional expectation would be also 0. Because if you take unconditional expectation of both sides, right, the expectation of 0 is 0, so the whole thing becomes 0. But then if you take unconditional expectation, a conditional expectation, it will become equal to xi t minus I, xi t. In other words, you get rid of the conditionality, essentially, and that would be also 0. So therefore, for all I larger or equal to 1, we will have that xi t, the forecast errors or expectation errors, are serially uncorrelated. They are not independent necessarily, they are uncorrelated. Often people talk about serial independence, but it's not really strictly correct. What we have shown that they are serially uncorrelated. Now, this step, I should have really included this property in the set of properties which I set out before. I think you better add it up to it, which essentially says that expected value of yt conditional omega t minus 1, it itself equal to expected value of yt. I forgot to include them there. This is valid for all cases. I mean, general property of conditional expectation. Okay? Now, as I said, these properties we are going to use both for solving rational expectation model, but they are also important for when we come to test the efficiency hypothesis. Let me say a few things about what is a martingale and what are the properties of martingales. Now, the classic reference I should say on this is Dobb 1953 book published by John Wiley. And there is a very good book which involves the application of martingale theory to central limit theorem and law of large numbers by Peter Hall and Hyde, who are a member of this department. So I think I recommend, but they are very difficult maybe to follow. I'm not going to use all of it. I just write down the things which turn out to be, the properties which turn out to be important for understanding of these solutions. Now, a process MT is said to be a martingale if expected value of absolute value of MT exists less than infinity, and if MT plus I conditional on information set omega t is equal to MT. Now here I have defined the martingale in a specific situation relative to our information set, omega t, right? Although you don't need to, you could define it much more generally as Dobb and others do. But for our purposes, since we will be always concerned with information sets which are increasing, they form an increasing sequence of sigma fields, and therefore it becomes a special case of the notion of martingale used in the literature. And another important point about this is that from this definition, we can right away realize that a martingale would have a constant mean. Why is that the case? Well, take expectation of this definition of what a martingale is and conditional expectation. We just said that if you take unconditional expectation of a conditional expectation, that becomes equal to expected value of mt plus I, and that's equal to expected value of mt. That is for all I, so therefore it should have a constant mean. Now let me just give you examples of a martingale. There are other properties which I'll come to, but let me just tell you what examples are there, so we can focus our discussion on a particular process, say. Now, any random walk is a martingale. If you write xt is equal to xt minus 1 plus epsilon t, you can see that it satisfies the martingale condition, assuming that epsilon t in this case would have finite moments. Not all orders, but just in this case, most situation we are in random walk will become a simple example of a martingale. Another way of writing it, this would be to write xt is equal to a constant, say k, plus epsilon 1 plus epsilon 2 plus epsilon t. That is also a martingale, clearly. Now, if I multiply everything by a constant, beta 1, beta 2, so long as I have got a certain condition on anxieties, on epsilon t's, again, I can get another martingale by even adding other terms into it. But I'm not going to discuss in detail all the various types of martingales. I mean, what is important to realize that there are many processes which can be a martingale, right? Now, what are the major properties of a martingale which we want to use later on? One is this one, that expected value of absolute value of a mt plus 1 is always larger than expected value of mt for all t. So what it means that a martingale would form is the mean, the expected value of absolute value of a martingale would be always rising as time t proceeds. And since it is always bounded, in other words, in mean it is bounded, so it would have would be bounded for all time t as well. That's an important property. Now, how can we prove that? The proof of this is, again, relatively straightforward given the conditions we have. We can start saying that, if you remember, we had expectation of mt. Let's start with that one. mt plus 1. We start with that. That is equal to expected value of, now it is a martingale, so that is equal to expected value of at time. Sorry, I should really start with t. That's equal to expected value of mt plus 1 given omega t minus omega t. Because if it is a martingale, so therefore mt, according to this, has to be written for all I, so it's also true for t plus 1. So we can write that. Now we can use the condition which we had, which said that I've wiped it off, which we said that the expected value of this absolute value is always less than or equal to expected value of, let me just write it correctly, so it's equal to expected value of mt plus 1 conditional on omega t. This is using the inequality rule we had before. Okay? Now, if we now take a conditional expectation of both sides of this inequality, remember when we take conditional unconditional expectation, the conditionality term drops out. So therefore, what we end up getting is expected value of mt plus 1, the conditionality drops out, has to be larger than or equal to expected value of mt, which we wanted. Okay? So that is true for all t again, since we did it for arbitrary t. Okay. This also suggests, as I said before, that it imposes a restriction on the moments of all the martingales up to the point, absolute values of makes the moments bounded, which essentially enables us to arrive at a certain conclusion when we look at a set of solutions of the processes which includes a martingale. Now, with these preliminaries, I can now look at the solution of rational expectation models with future expectation. I've already suggested how you could solve uniquely models which include current expectations. That is relatively trivial, and we discussed it. I'll come back to it later on when I look at the identification of rational expectation models. But it is the solution of models with future expectation which I now want to turn to. Let's start with the simplest model, which we have been looking at. And that is given by yt is equal to alpha, expected value of yt plus 1 given omega t plus wt. Now, the method of solution of this model has been discussed in the literature, the various methods, and some of the references I've already given the handout is Muth, first 1961, Taylor, Gurria, Lafont, and Montfort in Econometrics 82, and so on. I'll mention some of the approaches, but I can't really be comprehensive, and therefore I will just choose the solution methods which has been discussed in the literature, which are of interest, and I think it will relate to what we are going to do later on. Essentially, there are three approaches that one has been used to solve these sort of models. One is called the method of undetermined coefficients. And there are two versions to this method, application of this method. One in a time domain, another is a frequency domain. The time domain one was first introduced by Muth himself, and has been summarized in a little book by Whiteman. The second type of approach is operator method. You use a sort of like you solve difference equation. Use an operator, sort of a forward operator, if you like to call it, and then you obtain a solution of the model. And this has been done by Sargent and Schiller and Wallis, among others. Again, these are the references are in the handout. Finally, the third approach is the Martingale method, which I have applied and has been also developed by Gurria, Lafont, and Montfort in a very different way. Now, just to give you historical perspective of how these models have been solved, and then show you why these solution methods are not satisfactory, I first start with the Muth approach. But I will modify it so it is simpler to derive, and it's also in relation to what people like Sargent and others have done. And this is the approach which is most popular, and you see when you look at literature, although sometimes the way it's done is done in such a complicated way that it looks more complicated than it should be. The approach which is followed by Muth and Sargent and others is really method of finding a stationary solution of this equation. So it does not provide you with all the solutions. Now, the starting point is that WTs are usually assumed to follow a stationary, covariance stationary process, which can be represented by an infinite moving average process in terms of white noise errors. So therefore, one is usually assumed that WT can be written as AL epsilon T, where AL is the lag operator A naught plus A1L plus A2L squared ad infinitum. And we know that if WT is covariance stationary and linear, the Wald decomposition theorem shows that you can always write WT as this, and epsilon T is being white noise errors. Okay? So the solution approach really doesn't solve it for arbitrary WT, but it solves it for a particular class of WTs. That's the first problem with it. Although it maybe is a strength, when you're only interested in that sort of class of solution, it can be weakness if you want to find the general set of solutions to this problem. So the method is, from now, very straightforward. If we know that WT has got this representation, and since we are looking for a class of solution of YT which are also stationary, we can also use the Wald decomposition theorem to suggest that YT can also be written as, let me use my notation, as DL epsilon T as well. So you are making a shrewd guess of as what the solution ought to be. It's really the stationariness is fundamental to the whole of our approach. Now, if you assume, therefore, that the forcing variables are stationary and the output is also, we want it to be stationary, so you are looking to find out the operator function DL given the operator function of AL. Now, note here that since I have not imposed any restriction on the operator function AL or DL, it can be used to solve for any type of processes of WT, for example, ARMA and so on. So we can then use the solution approach here to find that particular solution when the process is in ARMA or whatever. Okay, so in that sense it's general, but in the fact that it concentrates on a stationary set of solution is specific. And it has to identify what the process generating WT is, which sometimes can be an advantage if we know what it is. Okay, to solve this, we just firstly, what we do, we just calculate YT plus 1 and take its conditional expectation, replace YT and the conditional expectation of YT back into here, and find out the operator DL in terms of operator AL. It's very straightforward. Okay, firstly, we write with YT is equal to D naught plus D1, epsilon T minus 1 plus D2 epsilon T minus 2, and so on. From this, if you then raise it to the, by one time period, expected value of T plus 1 conditional omega T becomes equal to, the first one would be D naught epsilon T plus 1 conditional on information omega T becomes 0 because it's white noise, okay? Because expectation of epsilon T plus 1 conditional on omega T is 0. So the rest would be D1 epsilon T plus D2 epsilon T minus 1 and so on. So that is the conditional expectation of YT plus 1 given omega T. We can write this in operator form. In operator form, we can write this as expected. Let me just write it again. what we do essentially, if you note, add d naught e epsilon t and subtract d naught epsilon t as we did in the first lecture. And then by making the right adjustment, you can write this as dl, operator dl, minus d naught multiplied by L minus 1 multiplied by epsilon t. Now, if we replace this together with what y is back in here, and also replace wt in there, we get an equation which looks like this, which is equal to alpha dl minus d naught L minus 1 epsilon t plus, now wt is also a stationary process assumed to be equal to al epsilon t. Now, by factorizing epsilon t, what we do, we equate the rest, the operators both sides, and we arrive at the solution that dl multiplied 1 minus alpha L minus 1 is equal to al minus d naught alpha L minus 1. Now, the problem is there is singularity here because when L is equal to alpha, that becomes 0, so this side will be 0. Both sides would be 0. Sorry, this side becomes 0, and therefore you cannot define d alpha. The only way to get rid of this singularity is also to make sure that d naught is chosen in such a way that both sides are 0. In other words, it would be 0 divided by 0, so we can cancel them out. Okay, and so therefore what we do, we evaluate this at L equal to alpha. That becomes 0. That's equal to A alpha minus d naught, because these two cancel, and that suggests that d naught has to be chosen as A of alpha in order to get the solution. And if we set d naught equal to A of alpha, assuming that is not 0 itself, so in other words, on the condition that A of alpha is non-zero, d of L becomes equal to A of L minus what we have, A of alpha, and then multiply both sides by L. Then we get L minus alpha. That becomes the lag operator which we need. Now, the only condition we need to assume is that value of alpha is less than 1. And that you need it in order to ensure that those lag operators actually converge. There is a convergence series. Now, if AL, as I said, is a moving average autoregressive scheme type process, so AL will be a specialized function which can be replaced here in order to arrive at the form DL. Now, this is a solution which people have used in the literature for different form of AL. But remember that we are using the same, we say that if Wt is a function of epsilon t, we are saying that also Yt is a function of the same epsilon t's and no other process, even if it's a stationary. It's not proved, but we have just assumed it. Okay? Now, in order to show the deficiencies of this, we need just to recognize that this is only one of many solutions. In order to demonstrate that this is only one of many solutions, what I suggest we do, we say suppose we call this solution Yt bar. In other words, let's call Yt bar being dl epsilon t, with dl being the value which we just calculated in terms of al. Suppose Yt bar is that. What I will do now, I'll demonstrate that Yt is equal to the Yt bar plus alpha minus t mt, where mt is a martingale, is also a solution of this equation system. Okay, a proof would be like this. First, we have yt1 plus 1 would be yt plus 1 plus alpha minus t minus 1 mt plus 1. So therefore, expected value of yt plus 1 given the information set becomes expected value of, given the information set, plus alpha minus t minus 1. But since this is a martingale, expected value of mt plus 1 conditional or omega t becomes equal to mt. Now, if we replace these values, these two expressions, back into the equation itself, we have that, since we know that yt bar is a solution, we can use this and suggest that it will satisfy the above equation. So therefore, we will get yt plus 1 minus alpha minus t minus 1 mt plus 1. I don't mean plus, sorry. It's just yt at the moment. This is the left-hand side. That is equal to alpha. And since this also is a solution, so I get that's equal to expected value of yt plus 1 given omega t minus alpha minus t minus 1 mt plus wt. Now, note here that alpha multiplied by this would cancel out with this side because of the Martingale property. So therefore, I'll get yt is equal to alpha, expected value of yt plus 1 given omega t plus wt. This and this cancel each other out. The result is that if yt bar is a solution, so would be yt. Now, you have noticed that there are many ways that you could specify a Martingale process. And furthermore, notice that the past history of the data, like y naught, y minus 1, and so on, doesn't put any restriction whatsoever on the Martingale process MT. If you start, say, yt naught here, what it tells you, it would be alpha to the power minus naught 1 and m naught. M naught is a process. You cannot define a process by a point. In other words, by knowing what y naught is, you cannot pin down the martingale which appears in the process. So you can therefore note that the approach adopted through the method of undetermined coefficient, it's successful to provide you with a stationary solution whenever it exists. Okay? And we already said that that solution exists, at least it's suggested that it exists, in this type of situation when alpha was less than 1. Now what I want to do is to follow a different approach and arrive at a solution to show you how this problem of non-uniqueness can produce ambiguity in the hypothesis of rational expectation as it presented. But before I make that conclusion, let's have a look at the operator method of solution. Let's go back and look at what the model was. We can first move the equation one period ahead. That gives us yt plus 2 given omega t plus 1 plus wt plus 1. That's straightforward. What we do, we take expectation of both sides of this equation, now conditional on information set omega t. So we get expected value of yt plus 1 conditional on omega t is equal to alpha. I'm now going to skip a few steps because imagine if you take conditional expectation of this using the iteration law, that becomes expected value of yt plus 2 conditional on omega t plus expected value of wt plus 1 conditional on omega t. What I've done, I've just applied the rule. Now, if I can carry on, I can replace that back in this equation. Now, everything becomes, yt becomes a function of wt and its conditional expectation and expectation of yt plus 2 given the information set. I can carry on till any point in the future that I like. Suppose I carry on to the arbitrary point in the future, t plus n. Okay? Now, what will be the result? If I can find it here, just towards the end. Well, I can't. I think the result would be, I have written it somewhere. I guess what my guess would be, maybe 1n of, it would be alpha to the power n expected value of yt plus n conditional on omega t plus I from 0 to n minus 1 alpha I expected value of wt plus I given the omega t. In fact, it has to be I from 1. I think that's right. Now, this method of solution, you'll see that now we have got all future expectations of the driving force or the forcing variables wt conditional omega t appearing in the model. And then, however, we have also this term. Now, the question is, under what condition I can ignore this term? You may be tempted to use the usual knowledge of solution of difference equation, in which that when you had the initial value, so long as alpha in absolute value was less than 1, you say if I go further enough into the future, n, remember now is going into the future, t plus n, if I go further enough into the future, this alpha to the power n goes to 0, so long as alpha is less than 1 in absolute value. Now, if I'm prepared to assume that my expectation of that very far future exists and hasn't blown up, I can ignore this term. Now, it is somehow having a belief in the future before you can arrive at a solution of today. And that is where the problem, in fact, lies. That we are not always justified in making such an assumption. Because after all, we are forming expectation. And to the extent that it is not possible, or the hypothesis of rational expectation, which endogenizes expectation, does not enable us to fix our expectation at some arbitrary time in the future, we cannot find a solution which is general enough for this model. We have to impose certain a priori restriction. If this equation had been derived from optimization principles, which I went through in the first 2 lectures, you found that this sort of condition, that the limit of this goes to 0, appeared as transversality condition. There we assume that the individual who optimizes, a consumer or an investor, an objective function or as an intertemporal decision process, has a terminal condition. In other words, we knew the time of when the consumer ceases to exist, or when the period of the horizon is ending. Okay? So you can think of capital N here as being the horizon, the time horizon in that type of optimization problem. So either we have to link the rational expectation equation to some optimization problem, or if we do not, and say that is one method of endogenizing expectation, the model is not determinate enough when you have got future expectation to provide us with a specific solution for you. They provide us with many solutions, which was presented in the adding up that Martingale. Now, in order to see how that Martingale process actually leads us to various types of solution, what I'm going to do is just to provide you with another type of solution which you can arrive. I don't have the time really to go through it. It is in the appendix of my own paper in Econometrics, Journal of Econometrics, 1981. If anybody's interested, can consult that appendix. But the solution, the general solution of this equation using the Martingale approach, can be written as yt is equal to alpha to the power minus t mt. We had that before, but then we will have minus lambda to the power minus t. No, sorry, I better write it in the second form. Sum of j from 1 to t minus 1 alpha to the power minus j and wt minus j. Using the Martingale approach, you can demonstrate that the general solution of this can be written in this form. Now you say, well, how this is related to all the many other type of solutions we have already arrived. It doesn't look in any way like the type of solution we have already encountered. Firstly, let me just point out that this includes all classes of solutions, so it's not one specific one. Second, it is valid for all processes of W. There is no restriction placed on whether W process here is a stationary or not. So long as it exists, the mean of it exists, conditional mean of it exists. Now, to arrive at the other type of solution encountered, what we need to do is just simply to replace effectively the martingale by a series of, if you like, equivalent martingales. Because if you remember, a martingale can be written in many different forms. You can have different processes which are all martingales, but they don't need to be exactly the same. You could have two martingales completely having different properties, apart from the martingale property itself. So what you can do, you can say, well, one would be to have what I've called to arrive at a forward solution, which is the same as the type of solution we would arrive if you had dropped the transversality condition, would be to say that if MT is a martingale, so is MTF, defined as MT minus expected value of alpha I, Wi, conditional of omega t, I from 1 to infinity. Now, to demonstrate that this is a martingale is very straightforward. Remember, this is I from 1 to infinity, so it doesn't depend on time. Okay? Because it does not depend on time, so this part is always a martingale. Remember, if anything doesn't depend on time, its conditional expectation would be always the same as itself, no matter what time. Since MT is a martingale, so MTF would also be a martingale. Now, we can replace MT from here back into this equation, since we want any martingale, so we can replace it in terms of MTF, another martingale, and then we arrive at what is known in the literature as a forward solution. I can write it on the top there. So what we get yt is equal to alpha minus t mtf plus j from 0 to infinity alpha to the power j expected value of wt plus j given omega t. The reason is that when you replace it back in here, all the terms from I to t minus 1, which is exactly the same as, because we know the information set omega t up to that, so we know all of them, will cancel out with this one. The only term which would be left would be those ones which are beyond the point in which we are starting, which is the stuff from j equal to 0. So you can see that, in fact, this would follow. So you can see this is, again, the same kind of solution we had, and it suggests now we can ignore this term again. But there is no guarantee in general that we could ignore the terms like this. We need to demonstrate that the martingale term should be dropped out when we deal with a solution. Now, incidentally, I need to assume that this expectation exists, and that will only exist for a general process, say W, if say W expectation of W exists and the process is convergent. And a condition for convergence of this is again that alpha should be less than 1. Now, what I will do now is prove an interesting lemma, which then enable us to arrive at a unique solution of a problem, of solution of the equation we are dealing with, when alpha, in fact, in absolute value is less than 1. And show you that in that situation we can ignore the Martingale term. This is sort of, if you like, a uniqueness theorem for stationary solutions. Now, remember, therefore, that we always can write yt is equal to some stationary solution yt bar plus a minus t mt, where mt is a martingale. Therefore, yt minus yt bar in absolute value is also equal to a power minus t absolute values of mt. We can take expectation of both sides. At is constant, it comes out, and we get this result. Now remember, if my alphas and a's are the same, so if you get confused, it's just exactly the same thing. I should say really alpha. If my alpha in absolute value is less than 1, it follows that alpha to the power minus t goes to infinity as t goes to infinity. Okay? Now, we know this is going to infinity, this part. However, we also know that expected value of absolute value of the martingale is always less than or equal to expected value of mt plus 1, and so on. So while this sequence is going to infinity, this sequence could never go to 0, because as t become larger, this value is also increasing. Although it's bounded, it never goes to infinity, but it still never goes to 0. So it means that this is going to infinity, and this is going to a finite number. So the only way that if yt is a stationary, this mean could also be, the yt, the new solution would also be a stationary. It's only and only if all the expected value of mt is equal to 0 for all time t. Because you can never have the situation, you can even write it in a more rigorous way. Say the supremum of this for time t is equal to the supremum of this for time t. And then, since this martingale expectation goes to a finite number, this always explodes. It goes to infinity. This side always goes to infinity. And you can also note that expected value of yt minus yt bar is always less than or equal to expected value of yt plus expected value of yt bar. This is always finite, because by assumption we have assumed that it has got it's a stationary process, so it's always a finite number. Now, because this is expanding, now this term has to also expand with the same rate, and this suggests that expected value of yt would also have to expand, which contradicts the assumption that we wanted to make sure that yt is a stationary. So the only way that we could get yt a stationary given yt bar is to assume that all of expected value of mt is equal to 0. Again, using the condition that this is an increasing function of time. This can only be so if mt itself is exactly equal to 0. Okay. If mt is equal to 0, then we know that we have established that yt is equal to yt bar. So there is only one unique stationary solution. If alpha is less than 1 in absolute value. In fact, you can generalize this result to higher order equations, but I'm not going to deal with them here. The idea is for you to get the gist of it. generalization of this to higher order is much more complicated. Now, so to summarize, the rational expectation solution for this type of models with future expectations would have a stationary solution if the forcing variables are stationary, WT. Second, alpha is less than 1 in absolute value. And the stationary solution which arises in this situation is unique. Now, this is why the transversality condition can be only justified if you are really assuming that the way the word works and the YT is generated is stationary, which is a phase before you start to model, right? So in other words, the rational expectation hypothesis is not strong enough for future expectation models to define the process so that it gives a definite answer. You need extra assumption, which is outside the hypothesis itself. Okay. So if you want to ask questions.